Welcome to the DESI Astro. In this Python tutorial on Astropy, uh, we are going to learn that how to do image convolution with a astronomical image. Okay, so convolution is a way to filter noise in a data with the application of 2D kernels. Okay, so your 2D kernels may be for this tutorial it's a Gaussian 2D kernel or another may be top hat 2D kernel. Okay, so and these kernels will be used to your filter noise in the data and making the images smooth in visualization. So let's do it. Okay, so for that I will be using Astropy Library, right? So here I can import libraries, right? So I will first I will be reading a fixed image file, okay, and then I will choose a source, and then I will do convolution with the kernel data. Okay, so let's first import some libraries. So import libraries. So I will import Astropy. So from Astropy dot input output import fits. So this will like used to deal with fits file, reading and writing the fits image file. And then you can import matplotlib dot pyplot as plt for your data visualization, and then you can import NumPy as np for numerical Python. So import NumPy as np, right? Now you can read the file. Okay, all right. So what I will do right now, I will read the image from a fits file. Okay, so I will give here file equal to fits.open. So this will open an image given a file name. So I will give here rcode.fits. Okay, this is my file name, and then you can get file information. So get file information. So you can get here file.info. So this is your primary LGO image, and it contains this much of your 1100 rows and 500 columns. Okay, so now plot this image. So plot this image data. So for that extract your data points. So you can call here image equal to file 0 for your primary HDU number, right? Then dot data. Okay, then plot this data. So for that type command plt dot image show, and give your image variable and run it. What is that mistake? Image show, there should be inch. Okay, so here you can see that there are some objects visible but not in much contrast. Okay, so go to the log scale. Okay, so for that type here library. So from matplotlib dot colors import log norm. Okay, so this will like make your this image on a log scale. So and type here norm equal to log norm, right? So see here you can see the image of the galaxy. Okay, and there are some objects. So what you have to do, you have to like convolve the this whole image with the different kernels. Okay, so let's do it. Okay, so do it. All right, so for what I'll do here, I will do convolution with this image and Gaussian kernel. Okay, Gaussian kernel, right? So for that I will be importing some kernels from the Astropy, right? So let's import here. So I will import some Gaussian kernels. So from astropy dot uh, convolution import convolve, right? So it will do convolution import convolve, right? Convolve, and then you can import your this two kernels, Gaussian 2D and top hat 2D. Okay, so you can import here Gaussian 2D kernel and then here top hat 2D kernel, right? Now I will do the convolution. So for that I will create a Gaussian kernel, right? So create Gaussian kernel, right? So I can create, say, Gauss. Okay, Gauss 2D, right? So for that Gauss 2D curve, then you can define your Gaussian 2D kernel as a function and see what it takes. So it takes your sigma in your x and y. So you can give only one value. So I will put here for both. So I can put here 3 and 3. Okay, for the sim, right? You can also visualize this Gaussian 2D kernel, right? So you can plot it. So plt dot image show Gauss 2D kernel, right? So here you can see that this is your Gaussian 2D kernel, right? Which have sigma equal to 3 pixel, right? So here 3 is pixel, right? 3 is pixel standard deviation, right? This is how your Gaussian kernels look like. Now I will convolve. Okay, so now I will convolve. Okay, convolve this data with Gauss 2D kernel, right? So what I will do, I will give a variable here, say, like I mean this basically this conversion is doing that it will like your smooth your data. Okay, so I will type here a smooth Gauss. Okay, so smooth Gauss equal to convolve, right? See what it takes. So give function. So it will take your array and the kernel, right? So type here. So your array is your image. Okay, so image, and then your and the kernel is your Gauss 2D kernel, right? So give Gauss 2D kernel, right? So this has done the job. Now plot it. Okay, so plot this image. So for that type here plt dot image show, and you can give here a smooth Gauss, plot it. So here you can see that now your object has been smooth. Okay, you can see here, right? Maybe if I don't put a log norm here, you can also see. So just put a log norm. Okay, so see here. So put here norm equal to logner and see the data in them. Okay, so here you can see that this image is looking much smoother than this image. Okay, this is like noisy image. This is your much more smooth image. You can also see the core of these galaxies, okay, in a smooth fashion, right? Or maybe you can do one thing, just don't put here log norm, right, and just put the image here as it is, and also here. See, you can see here like nothing much is visible, but here you can see that your image is like visible and it has been smooth compared to your background and noise data, right? So this way you can put, and then you can write a title here, plt dot title, like Gaussian 2D kernel smoothing, right? This way you can do here. You can type here plt dot show, right? This is how your smoothing looks like. Okay, now we have done this Gaussian, right? Now I will be doing using this top hat 2D. Okay, so let's do it. So what I will do, I will do convolution with top hat 2D kernel, right? So for that I will define this kernel. So I will type here top 2D and kernel, right? And then I will give top 2D kernel and see what it takes. So it will take the radius. Okay, so radius you can give anything you want. So I will give here, say 5. You can give it 5 pixel. See, it's a 5 pixel radius. Then you can plot this kernel image show and top hat. What is the mistake? There should be SHO. Okay, so see how it's look like. Okay, you can also increase stuff you want. So this is how it's look like, right? So I will give 20. So it's like 20 radius. Okay, now I will convolve. Okay, so I will do filtering with data and filtering of data data with kernel, right? Then okay, then I can define here top smooth. Okay, top 2D smooth variable, and then type here convolve, give your image data and your kernel, right? So top hat 2D kernel, your job is done. Now plot it. Okay, so plot a smooth image. So for that, type here plt dot image show and give your 2D array top 2D smooth. Run it. Okay, so here you can see that you can see like much better picture compared to your Gaussian 2D kernel, right? So here like images are like small. By convolving with your 2D top hat 2D kernel, we are like getting the better images, okay, of the object. So in this way you can smooth your galaxy image or star image using Gaussian 2D and top hat 2D kernel, right? So this is a like way to filter noise from your astronomical images by using convolution and the filtering. So it depends upon like which filter you use, you will get a different result. So for that I have used only two filters, Gaussian 2D kernel and top hat 2D kernel. They are used to smooth your data. So here's the code once again. I have it a fit file simply plotted. Then I have applied two different Gaussian, I mean two types of kernels, Gaussian 2D 33 pixel, and we have mm, top hat of 20 pixels, right, of radius. So this will do the job, and here's the result. So you can give a title here, plt dot title top hat 2D kernel a smooth image, right. So this is how the image looks like. Okay, this is your original image. This is the Gaussian kernel. This is a top hat, and this is your smooth images using top hat 2D kernel. This is using Gaussian kernel. So you can explore the difference between these two, that how they are going to make difference. So thank you.